Hi, welcome to these notes in our thermochemistry unit on enthalpy. Enthalpy also is a way to express the amount of energy per mole of a substance. And so it kind of goes along with what we were learning before, except for what we were learning before was how to use the process of calorimetry to experimentally determine the amount of energy that we get from a reaction or a chemical process or a physical process. In enthalpy are actually scientifically accepted values for specific items. So enthalpies have been experimentally determined and they're scientifically accepted. An enthalpy value is actually the heat energy content of a system at constant pressure. This is very similar to like the accepted value for the amount of energy you should be getting. Because we know that we're going to have some loss of product or heat due to surroundings and things like that. But scientists have been able to truly try to determine how much heat can I get per mole of reaction or reactant that I'm starting with or something along those lines in trying to create good experiments that minimize heat loss to surroundings and things like that. So a lot of times you will hear that we use heat and enthalpy interchangeably, and that's what the delta H is for. But delta H really means enthalpy. And so heat is really the Q. But when we're talking about enthalpy, it's really Q per mole is really what it is, because we have to be specific. A change in heat can be measured during a reaction or a physical change, and then if you divide it by the moles of reaction to find the enthalpy is in the units of kilojoules per 1 mole. So that's why it's a scientifically accepted value, because it's saying, let's say a physical change. If I heat 1 mole of water, it would require a specific amount of energy to do so. But if I had 3 moles, it would be 3 times that amount of energy. So this is really looking at per 1 mole of a substance. But a lot of times it's difficult for us to know the exact value for enthalpy, mostly because scientists are experiencing. The only way to know enthalpy or the amount of energy is to experiment. So experimentations are always going to have some flaws. So even though many scientists have conducted these experiments, experimentations always have some small flaws. Or errors that are beyond human control, especially when you're experimenting with energy. It's very hard to make sure that the energy stays in the calorimeter and does not dissipate to the surroundings. And so there's a lot of extra calculations beyond just using Q equals MCAT, because you also have to consider the cup. If you are using a coffee cup calorimeter, that also absorbs some of the energy. And there's lots of things that go into it, into the true calculation or the accepted values of enthalpy. But the accepted values that we use are better or more complete because scientists have developed experiments to give us better information than what we would do in lab, because we would see a lot of loss for heat in a lab, even if we were using a good calorimeter. The enthalpy of the reaction is expressed as delta H, and then what we do is we use little subscripts at the bottom. Now the subscripts are important because they kind of tell you what's happening. So delta H means enthalpy, the RXN means reaction, and we use different ones for different kinds of reactions. Not all of them have that, but the enthalpy of reaction is the heat absorbed or released from a chemical reaction when it's at standard temperature and pressure. Most of the time, the units are kilojoules per mole. And just like we learned before, we can have positive endothermic enthalpies and we have negative exothermic enthalpies. So putting a sign on the enthalpy helps you determine, is it releasing or absorbing energy? So synthesis is the formation of the product. So this is a delta HF. The F is actually for heat of formation. And so it's based on whatever you are forming. So if you are forming carbon dioxide, then the enthalpy is the amount of energy it takes or it releases to form carbon dioxide, 1 mole of it. Decomposition, we don't really have, I mean, I guess you could write delta H decomp, but typically you won't see that. So delta H reaction, we just kind of use generic term. Combustion does have its own. Typically, these are the two most used ones in science. So typically textbooks specifically say delta H formation, delta H combustion, and then all other types of reactions, we just kind of generic delta H reaction. But the formation and the combustion ones are the most common ones that you would see. All right, so when you're doing a thermochemical equation, we've talked about this before, but we're going to add a little more to it. Thermochemical equations are how we actually express the heat in our balanced chemical equation. So the reaction in a hot pack, we'll think about it. If your hot pack is releasing energy, right? So the hot pack is releasing energy because that's what we feel. So then you know that it's exothermic. That's actually a chemical reaction. There's a couple different kinds of chemical reactions. So I just use the dissolution of calcium chloride, which is the one we did in lab. But you can have negative delta H for the exothermic reaction. So there's two ways to write the reaction or to indicate what the actual amount of energy released in that process is. So you can either do it the first way, which in this case, then you include it in your reaction. So since it's exothermic, heat is a product. So heat should be released as a product. So then you will see right here that we write the energy into the equation as a product. Okay? If you see energy as a product, that indicates that it's exothermic. The other way that is, I feel like, more common now in textbooks and things like that is that they do not actually include the energy inside the reaction. They separate it out, but then it just looks like a quantity of energy. So they put the negative sign on here to indicate that it was released. So remember, we use the positive and the negative signs to indicate that it was released. In a chemical reaction, chemical reactions are always positive values. So in this case, we don't put the negative sign because we're showing it as a product. And that's the difference. So we would have as a product, it's going to be written positively. But if we write it outside of the equation, we would include that negative sign to make sure people understand that it was a product. And so one of the things you'll see over here, this is a potential energy diagram, which allows you to see. So here's my energy starting off of my reactants. And so we do see that my energy goes up just a little. This is called energy of activation. All experiments and reactions require a small amount of energy to get started. And then what ends up happening is my energy left of the products is down here. So when I compare the net energy change, so I'm ignoring the energy of activation because I used that, but then it came back out. So that didn't make a difference. This part right here is the actual amount of heat released. My reactants decreased overall energy to form the product. That means my delta H would be negative. So I lost energy, and so that's how we know. So the enthalpy is the difference between the two. So if I take products minus reactants, so you can find delta H by taking the products minus the reactants. So final minus initial kind of again. So if we take the energy of the product minus the energy of the reactants, we would get a negative value. And that's where we get our exothermic reaction. It tells us that we lost energy. Okay? The reaction in a cold pack is the opposite. It is absorbing energy because it absorbs energy from the environment around it so that it feels cold to us. So similar to how like a refrigerator would work. So positive delta H value would be written if we look at our thermochemical equations. If you look at the second equation, when we write the energy or the enthalpy outside of the equation and we write it off to the side, we put the positive so that way we can say that this is endothermic. That tells somebody that it's absorbing energy. But when we write it on the inside, as in this first part, heat is a reactant or going in. So notice we wrote it right here. Again, as a positive value, because anytime you write it inside the reaction, it's always going to be a positive. But it's showing that the ammonium nitrate plus the water plus 129 kilojoules made the ammonium nitrate aqueous, which is really just ions. Okay, so let's look at this and what's happening. Here's my reactants. Here's my products. Remember that this is the energy of activation. We don't really care about that. That's not really that's the amount of energy we have to put in to get started. But what we do care about is this difference right here. So when we compare this part, this is the delta H for the reaction. And in this case, my overall energy went up. So it's positive. So we know that the enthalpy of the reaction is positive, so that makes that endothermic. So the potential energy diagrams can also be used to figure out if something is endo or exothermic. So if we look at this potential energy diagram, it's just showing you a couple different ones. So again, shows the energy of activation. So remember that this is showing you that if you add a catalyst, what a catalyst does is a catalyst actually brings this down. And so it takes less energy for the reaction to get started. But the overall portion that we care about in terms of energy is this part. This is my delta H. And in this case, products are lower than reactants. So that means we had to have lost energy. It's got a negative delta H. So this is showing an exothermic potential energy or reaction. So that's understanding the basic background. Now, how can I calculate enthalpy myself? That's what we're going to learn on the next page. All right, so when I'm calculating enthalpy, enthalpy calculations use stoichiometry and delta H to find the total energy that is released or absorbed during a chemical reaction. So here's an example. Upon adding solid potassium hydroxide pellets to water, the following reaction takes place. So really keep in mind this is really K plus and OH minus because it's aqueous, which just means dissolved in water. So the solid is dissolving, and in this case, it's positive 43. Okay, so let's think about what's happening. Where do we see the energy? Is the energy a reactant or the product? The energy here is a product, and it's inside the reaction, so that's the only reason that it's positive. It does not, the positive, when we write it inside, the reaction does not tell us anything about endo or exothermic. We have to look at where it is. When energy is a product, this tells me that it is exothermic. So is the beaker going to get warmer or colder? Well, if the reaction is releasing energy, my beaker should get warmer. We should feel more energy in the surroundings. So what is the total heat that's absorbed or released for the dissolution of the 14.0 grams of KOH? Well, first off, we know that it's released because we just figured that out by saying it's exothermic. So what's the total dissolution? Well, remember that this is the kilojoules for 1 mole of this, right? So we have to use our stoichiometry here. So when I use my stoichiometry here, I have to consider that I have 14.0 grams of KOH that I'm going to dissolve. And so initially, my 14 grams, I have to convert to moles. So I'm going to have 14. I have to convert grams to moles, so I need to use my molar mass. So my molar mass of KOH is 56.1 grams of KOH for 1 mole. So this tells me how many moles of KOH that I have. Now we're going to use a mole ratio. Now this is interesting because my mole ratio is not what we typically think. Now I'm looking at the mole ratio between KOH and energy. So 1 mole of KOH is 43 kilojoules of energy. So 1 mole of KOH comes down and I can get to the 43 kilojoules of energy. So this is stoichiometry. It's just not comparing mole to mole. Now we're comparing mole to the energy in the reaction. So this would actually tell me the total amount of heat. So I would take 14 and I would divide it by the 56.1 and I multiply it by 43. And I wish I would do that correctly. I didn't do it correctly in my calculator. All right, and so when I do that with sig figs, I want 3. So this is going to be 10.7 kilojoules released. Well, I can write released, or I could write just a negative sign here, and that indicates released. So that way I know that that amount was released out of it. So you don't have to do both. You can either do negative or do released. It means the same thing. All right, so I want you to try the next reaction I gave you, the next two on your own, and see if you can figure them out. They're very similar. The only thing that we did differently in the practice problem 2 is that I give you the kilojoules per mole. And so in this case, this is the ratio that you're going to use, or the relationship. So you actually, this is forming, so this is per mole of NO2 that this is per mole of NO2 that you are forming. So you're going to actually use that to figure out your total amount of kilojoules that are released. So you're going to have to do the stoichiometry, but you're going to be comparing the 2.30 moles of nitrogen dioxide. You really, in this case, don't need, I don't think, your amount of you don't really need your chemical equation because it already told you how much was released per mole. So you're really just using the ratio that it provided you instead of having to use the equation. But on this one, you would have to do some stoichiometry with the equation. All right, so try practice 2 and practice 3, and we'll look at those when you come to class next time.